This lesson deals with a basic differential amplifier. You can find these notes in the ECE302 ebook in Chapter 6, starting on page 4. What's shown here is a schematic of a basic differential amplifier with two inputs and two power supplies, a positive power supply and a negative power supply, and two equal resistors, but also two identical transistors. You fabricate the transistors on the same piece of silicon, they are very, very close to each other. If you were just pick two transistors out of a parts cabinet, they most likely wouldn't be. Let's analyze this amplifier using our four-step procedure. Our first step is to assume that we're in the active region and to put in a DC model for each component. We'll set the AC source is equal to 0. I have a resistor R sub EE up here in series with this battery, and I have these two resistors with this battery, and then between the base and emitter of transistor 1 would be our VBE on 1, and between the base and emitter of transistor 2, VBE on 2, if we're in the active region. And then between the collector and the emitter of transistor 1, we have a current source of beta FIB1, which would be the current coming into the base of transistor 1. And likewise for transistor 2, between the collector and the emitter, we have a current source beta FIB2, where IB2 is the current entering the base of transistor 2. If we're in the active region, the base current is approximately I sub S over beta F times e to the VBE over A to F E sub T. I'm throwing away the smaller terms here, but this would be dominating those expressions. This circuit, I don't really know the value of VBE on 1 or 2, but I do know that they're actually the same value because they're hardwired together. There's a common wire here, and then by setting the source equal to 0, we're connecting the positive terminals to each other back to ground. Whatever VBE 1 and 2 are, they're the same value. But since the transistors are identical, their I sub S's are identical, and then back in this expression, that would then be with identical voltages, it would give you exactly the same base current in either transistor. And likewise the same collector current and the same collector emitter voltage, independent of whatever the value of VB on is. Let's solve for this current, so we can eventually solve for the base current. This current is equal to the emitter current of transistor 1 plus the emitter current of transistor 2, but since these are equal to each other, we'll call that twice I sub E, or we'll drop the subscript in that IE1 equals IE2. The emitter current, that's over here, is the base current times beta F plus 1. I'll multiply that by 2. And that's equal to the current in this resistor with the direction indicated. That's going to be this node voltage, which is minus VB on 1 or 2, or just call it minus VB on in general, and then minus a minus VEE, which becomes a plus VEE, divided by the resistor REE. Now we can solve for I sub B. In this expression, I sub B is equal to VEE minus VBE on, divided by 2, the quantity beta F plus 1, and then the resistor REE. And if we're in the active region, then the collector current is beta F times that. Lastly, let's solve for the collector emitter voltage. Let me scroll back up here. We can solve for either one because they're going to be identical. The collector emitter voltage is going to be this node voltage minus this node voltage. I have a current coming in here. That current times R sub C is going to give me a drop in this direction. So this node voltage is minus I sub C times R sub C, and then plus VCC. And we're going to subtract this node voltage, which is a minus VBE on. And that's what the expression is on the next page. Collector emitter voltage of either transistor is minus the drop across R sub C plus the positive battery, and then minus the minus VBE on. Our second step in our four-step algorithm is to calculate the AC model. We're going to calculate R pi, which should be R pi 1 and the same as R pi 2 because we have the same biasing points. That's going to be A to F V sub T over I sub B at this operating point, and then our AC beta will be the same as our DC beta. Step 3 is to then find the AC results. So we're going to put an AC model in for each component. So we had a resistor R sub C and a resistor R sub B. Then there was a battery here. So we set that equal to 0 or short. There was a battery here. I'm going to short that. And then we're going to put our inputs voltages here. Here's V1 and here's V2 on the input side. And I'll draw that as a sum and a difference of a common mode signal with the differential signal divided by 2. And then here's the differencing with the minus sign. Between the base and emitter of transistor 1 is R pi 1, which is the same as just R pi. Put that there. And then likewise here for R pi 2, just call it R pi. And then between the collector and the emitter, I have a current source of beta F IB1. I have to show where that is, and IB2 for this transistor. And these are our phasor currents, and we're doing an AC analysis. Now, there aren't any capacitors here, so we don't have to deal with mid-band analysis. To use the ideas of symmetry that we talked about in the last video, I need to be able to draw this as a circuit in two identical boxes. But the problem is right here. I've got this resistor that's hooked up on this side and this side. So what I'm going to do is I'm going to draw this resistor twice and double its value so that when they're put in parallel, I just get half the value. Let's take a look at that on the next page. Here's the model for transistor 1. Here's the model for transistor 2. And then I drew this resistor with twice the value so that when you put these together in parallel, you just get REE. Now I've got two identical boxes that are mirror images of each other with our input 1 and our input 2. I'm going to use superposition to find the output voltage Vout1 and Vout2. Let's do the right-hand side of this. Let's set the common mode signal equal to 0 and find the output voltage Vout2 due to this VID over 2. And then we'll use that to find Vout1. If you recall from our last video, any common wire, when you have a differential signal, is sitting at 0 volts. So I'm going to replace that by a short circuit, shown over here back to ground. That short circuit shorts out this resistor 2REE. Let's redraw this. I have a lot of grounds in this particular picture. I have a voltage source VID over 2 between this node and ground, and then I have a resistor R pi back to ground, and this is right here. On the other side of this, where I have Vout2, this is due to the first source. There's going to be a current source back to ground, a beta F IB2 prime, and then a resistor in parallel with it, R sub C, it's from here back to ground. And my voltage from here to ground would be Vout2 prime, again due to the first source. The analysis is pretty simple once we can get rid of a big chunk of our circuit. Our output voltage is going to be equal to the current flowing into this resistor, which is minus beta F IB2 prime times the resistor R sub C. But what's the current IB2 prime? It's going to be equal to the voltage applied here divided by the resistance. That's VID over 2 divided by R pi. And now I can pull that out over here, and I've got that Vout2 is equal to minus beta F times R sub C divided by 2 R pi. Because of the symmetry I have in the circuit, I can find Vout1 prime due to the input of VID over 2 with the sign flipped. It's going to be the same value as this, but changing the sign of it. Taking the negative of our last result, I think in a positive beta F R sub C over 2 R pi times VID. Now let's also find the input resistance of this half circuit. That's going to be equal to this voltage divided by this current. That's what's on the next page. So the input voltage divided by the input current is just equal to R pi. Now how does that relate to the differential input resistance? Let's go back to our circuit and just draw it as a rectangle here. This will be our whole circuit. I've got VID over 2 on one side and minus VID over 2 on the other side. The difference of these two would be this term minus this term, so I would get this term twice. The voltage across here would just be VID. I have a current I sub B2 prime coming in here. I have a current coming in here I sub B1 prime. But we know because of the change in sign here that I sub B1 prime is the negative of I sub B2 prime. If I sub B1 prime is entering, then minus I sub B1 prime is leaving. What's coming in is IB2 prime, and what's going out is IB2 prime. The ratio of that voltage to the input current that goes in and out would be the differential input resistance. So I can solve for this expression by finding VID. From over here, it's going to be equal to R pi times IB2 prime times 2, and then divided by I sub B2 prime. Those two cancel, and I get twice R pi. If I find the input resistance of the half circuit, the full circuit is twice the value. And we kind of did this symbolically here, and this is going to be true for any differential amplifier. We found the differential mode gain. Let's find the common mode gain. We'll again do superposition, but now we'll set the voltage source VID over 2 equal to 0. I'll use the right half side of the circuit for the analysis, but you could do the left hand side too. So here I have V sub IC, and my VID over 2 is set equal to 0. If you recall from our last video, when you have common mode input signals, then the common wires are just simply cut because the current in them is equal to 0. I have V sub IC to ground. I have R pi then connected to 2REE, and then I have my output voltage Vout2 current source back to this node with R pi of beta F IB2 prime, and then a resistor back to ground. We're drawing this with just one ground symbol. This voltage is going to be equal to the current that flows in this direction, which is going to be a minus beta F times IB2 double prime, and then times the resistor R sub C. Let's solve for I sub B2 double prime. The rise in voltage here is V sub IC. The drop is I sub B2 double prime times R pi. And then what's in here is beta F plus 1 times IB2 double prime times 2REE. So then solving that equation for I sub B2 double prime, we get V sub IC divided by R pi, and then 2REE multiplied by beta F plus 1. Bring this over here, bring the R sub C here and the beta F. Vout2 double prime due to VIC is equal to beta F RC over R pi plus 2 times the quantity beta F plus 1 times REE. Having the result of this half circuit, we can predict the other half circuit, which would be Vout1 due to the second source, double prime. It's just going to be the same value as here, no sign change. Next thing I want to find is the input resistance of this half circuit. That's going to be the ratio of this voltage to this current. And we sort of have this already right here, with the equation we wrote around this loop here. that this voltage is equal to this current times R pi, and then I have beta F plus 1 times this resistance. The resistance looking in here is going to be equal to this resistor plus this one multiplied by beta F plus 1. That was his expression right over here. Let's take a look at that on the next page. Now, how does this half circuit input resistance relate to the full circuit's input resistance? Well, let's find the resistance looking in due to the common mode source. I'm just going to draw this with just one source here. And here's my VID over 2 and minus VID over 2 set equal to 0. And I'm now going to find the ratio of this voltage to current. Well, the current coming in this side is IB2 double prime. And the current coming on this side is IB1 double prime. But because we have the same sign on both our inputs, these two currents are equal to each other. The current I sub IC is just simply the sum of these two currents, which is the same as doubling I sub B2 double prime. R sub IC is the ratio of V sub IC to I sub IC. Here we have I sub IC and V sub IC, so let's solve that equation. V sub IC divided by I sub IC would be taking the reciprocal of this denominator and dividing by 2. That would be R pi over 2, beta F plus 1, 2 divided by 2, and REE. This would be the resistance of the half circuit divided by 2. There was half of the half circuit. This will always be true for common mode input resistance. Now let's add our results together to get our output voltage. V out 1 is due to V out 1 prime plus V out 1 double prime. And that's going to be equal to beta F RC over 2 R pi times V sub ID. And then minus beta F RC over R pi plus 2 beta F plus 1 times RE times V sub IC. And then V out 2 is the same term here, but with the opposite sign, with the same sign here. ADM is going to be equal to a minus beta F RC over 2 pi. We defined it with V out 2. And this term over here is going to be A sub common mode, which is, again, a minus sign, with the beta F R sub C divided by R pi plus 2 times the quantity beta F plus 1 times REE. Let's put some numbers in to see what we're talking about in terms of gains for a typical amplifier. Suppose we used 15-volt power supplies, and that beta F is 50, and V beyond is equal to 0.6. Beta F is 1, R sub C is 75K, and REE is 70K. Our equation for I sub B was VEE minus V beyond over twice the quantity beta F plus 1 times REE. Putting in 15 volts here, 0.6, 50 here, and 70K, I get 2 microamps. Multiplying that by 50, I get 100 microamps. The collector emitter voltage is equal to minus R sub C times I sub C plus VCC plus V beyond. 100 microamps times 75K with a minus sign plus 15, and then 0.6 is 8.1. So it is in the active region. R pi is A to F V sub T over I sub BQ, and that's 13K, using an I sub BQ of 2 microamps, and an A to F of 1, and a V sub T of 26 millivolts. ADM was minus beta F RC over 2 R pi. 50 times 75K divided by 2 and 13K, I get minus 144.2. R sub ID is twice R pi, so twice 13K is 26K. The common mode gain, though, is this expression, which is 50 times R sub C, which is 75K over 13K plus 2 times the quantity 51, but then times 70K. It's actually a number less than 1 in magnitude. It's actually minus 0.524. Differential gain in magnitude is much bigger than the common mode gain. That's actually a good thing. We'll talk some more about that in the next topic. And then lastly, R sub IC is R pi over 2 plus the quantity beta F plus 1 times REE. 13K divided by 2, then 51 times 70K is 3.576 megohms. Very big common mode input resistance and a not so big differential mode input resistance. There's another term that we talk about with differential amplifiers and ultimately op-amp designs. It's a thing called common mode rejection ratio. This is the ability of the amplifier to reject common mode signals. We saw in this last example that the common mode gain in magnitude was much smaller than the differential mode gain. We're going to define the common mode rejection ratio as the ratio of the differential mode gain to the common mode gain in magnitude. In our last example, that was a minus 144.2 divided by a minus 0.524, just taking the magnitude is 275.2. Ideally, I'd like the common mode gain to be 0. Of course, to pass no common mode signal, but just simply take the difference of the two. Of course, that's what we were talking about with op-amps in previous courses. The one way to do that is to look at the expression we had for the common mode gain, and we could make that smaller because the term REE was in the denominator, but it wasn't in the term for the differential. One way to increase the value of this is not to use a voltage source for biasing with a resistor, but to use a current source. We'll take a look at it in the next video. This is a basic differential amplifier.